Hello all. We're going to be taking a little bit of a break from new Calc 2 stuff, and we're going to look at some exponential and growth and decay models, which is a little bit of a review of pre-calculus and Calc 1 as well. So when we say exponential, we're talking about something that is in our exponent, and right here, this equation is what we call continuous. Sometimes people will remember it as p and then e to the rt, but this k and the r are the same. This y sub naught is just saying our initial value, which is what this p stands for. A lot of times it stands for principal. And we use this all the time when we're talking about population growth or the way bacteria grows, half-life, double life, things like that. Our first equation actually deals with bacteria. So this actually asks us two questions. How many bacteria are present after 5 hours? Well, 5 hours is the same thing as 300 minutes. T is measured in minutes. So all I need to do here is plug in 300 for my T, and I get about 80,685.7587 bacteria. In homework, it'll usually tell you how many decimal places to round to. You can always not round and enter in the whole answer if you would like to as well. Okay, second question, when does the population actually reach 10,000? Well, that's not my T, that's actually what my f of x is. Sorry, 100,000. So 100,000, and I'm looking for when that happens. So my t is just going to stay as a t, and that's what I'm actually going to solve for. When I divide by 200, I should get 500 there. Yep. And then e to the 0.02t. Now this is where ln's are super, super useful because they are inverses of this natural log of e. So if I was just going to say ln of x, that's the same thing as saying log base e. So this e that is our base and ln will cancel each other out. I can do that on both sides. So I will have ln of 500 is equal to 0.02t, and all I need to do now is divide by 0.02. So just plugging that into Desmos, we can actually see that our t value, or how many minutes we're going to be waiting for the bacteria to reach that amount, is going to be just over 310 minutes. I want to talk about this idea of compound interest too. So usually banks use this all the time. Savings loans, they use something called um, amortization, which is like a form of compound interest. So usually how compound interest goes is we have an amount that we're putting into our account, and then we have 1 plus whatever our rate is, usually divided by the number of times it is compounded monthly, and all of that is raised to the n times t. So if this is compounded monthly, our n would be 12, and our n up here would be 12, and it would compound 12 times for however many years that we have, and that would give us our amount that we have right here. I want to play a little fun game. I actually want to look at what is happening to a function if I just say, like, I invest $100 into an account that is earning 100% APR. I want to see what happens when we invest, let's just say $1 to make it easy, at 100% APR for 1 year. So what I have here is it compounding more and more often. This first one, it's compounding annually, semi-annually, so twice a year, monthly, so 12 times a year, daily right here, which that's what credit cards compound. And then let's just do every hour. So I'm going to multiply this by 24 and multiply this by 24. And this number kind of looks like it's starting to approach something. So I've made a new equation over here where n is a slider, and I'm actually just going to slide it up to, even by the time that we get to it's compounded, this many times in a year, you can see that this is starting to approach some value. And that value is pretty close to our value. Actually, it's exactly our value of E right here. So if I go a few, it's compounded a ton of times, you'll see that our values are very, very similar to each other. That's what continuous compounding actually means. So in other words, our definition of E is our limit as n just keeps on compounding. It's compounding continuously here and here. That's our definition of E. And finally, we have that equation that I just gave out at the very beginning of class. So let's actually try using it. Let's try using it in this example. We have a 25-year-old that is offered an opportunity to invest some money. That sounds great. Usually they're trying to borrow money at 25, and so that's the opposite of investing. But if you ever get an account that pays 10% annual interest, oh my gosh, it's really, really good. Stock market is between like 5 to 10% annual money that you get back. How much does this student need to invest today to have $1 million when she retires at age 65? So from 25 to 65, that is a total of 40 years. And when she turns 65, unfortunately, $1 million won't be enough to retire, or it won't be as much to retire as it is right now. So that's the balance that she wants is $1 million. And then she doesn't know how much she is going to retire now. She just knows what her end goal is. And I'm going to have this as e to the, I know this is 0.05, and then my time is in 40 years. So I can find what this value is right here, e to the 0.05 times 40, and then actually divide that over, and I will get that p is equal to, this is how much money she has to invest at age 25. Just a casual more than 100 grand, which is pretty crazy. But she'll just let it sit there. Doesn't have to put any more money into it, and she'll have $1 million in 40 years. What if she actually earns 6% annual interest compounded continuously? Well, our problem is set up exactly the same, and it makes sense that if we have a higher percentage, that we're not going to have to put quite as much money in there in order to reach that $1 million. We'll reach that $1 million faster, but since we have 40 years as our time constraint, it just means that I won't have to start out with as much. So when I divide this e to the 0.06 times 40 over, I'll have 90, so 717.95 that I have to, or that she'll have to invest. So think about it, that's just 1% over the span of 40 years. And the difference that you are actually investing is more than 40K. This doubling is used a lot when we're talking about in physics or chemistry, the time that it takes bacteria to actually grow. So if y naught is what we're actually starting out with, it could be 1 bacteria, it could be 10 bacteria. I'm just going to say that double y naught is what we are actually going to have at the end. And if this was 10, then this would be 20, and I would divide by that number. And the same exact actually thing happens here, is that I am looking for my double time, which means it doesn't really matter what my start value is. I'm looking for when this e to the kt actually doubles or becomes 2. If there's kind of an invisible 1 right here, it's when that 1 is doubling to a 2. So I can find, I'm looking for this in terms of k. I can find this by taking my natural log on both sides, and I'll have natural log of 2 is equal to natural log of e cancel out, and I'll have k over t. So really, to solve for k, all I need to do is divide by t, and it is equal to ln of 2 over the amount of time that it would take to double. Just like we have double life, we also have something called half-life, and that would be considered exponential decay. So if we started out with like 10 bacteria, exponential decay or half-life would be when there are 5 bacteria or half that amount. And our key value would actually be negative there. So we call that a decay. graphically, it also makes sense. It's looking something like this. Newton's law of cooling actually has to deals with that exponential decay that we have right there. So I'm going to take this equation and we're going to look at our problem right here. According to experienced baristas, I used to be a barista, the optimal temperature to serve coffee is between 155 and 175, which is true. Suppose coffee is poured at a temperature so it's really too hot to drink, and after 2 minutes in a 70-degree room, it has cooled off from 200 to 180. So one of the first things that we want to do here is figure out what we're actually trying to find. When is the coffee first cool enough to serve? So first cool, I'm looking at when it's going to reach 175. That's like my tea temperature here. It's equal to, and then now I have my initial temperature. Well, my coffee started out at 200 minus this A is my ambient temperature of the room, which was 70. Also 70's out here. And then I have e to the negative k, and then t is when it's, we don't know. We're actually just trying to find that. So we have k and we have t that are both unknown here. So maybe before we actually try to find when it is cool enough, we could use this 2 minutes that it has cooled off to 180 to find, ooh, my k value will be constant. So I'm going to set up the same exact equation, except that now I know that after 2 minutes, so t equals 2, that I will have 180 degrees right over here. And I'm going to try to solve this out. I'm going to simplify my coefficient out in front, subtract 70. Go ahead and pause this video and try to solve this. And now I just feel like I'm on repeat because I've done this so many times with ln. Before I take the ln, I actually want to divide by 130. And now I'm going to take ln on both sides, ln on both sides, and my ln and my e will cancel out. I'll have negative k over 2. And I can solve for that k value by dividing by negative 2. So k is equal to ln of 11 over 13, which I could write as ln of 11 divided by ln of 13 if I didn't want to have a fraction right there, and then that is over negative 2. So that is my k value that is going to go right up here. Okay, I've plugged in that value for my k. And I do have a negative and a negative, so I'm going to cancel those out. And I'm solving for t, so I need to get this e to the whatever by itself. I'll divide by 130 and then take ln of both sides. So it looks like I just need to take ln of 12 over 26 and divide by ln of 11 minus 11 of 13 over 2. Or I can multiply by 2 and not have a fraction over there, and now just divide by ln of 13 minus ln, or ln of 11 minus ln of 13. And you can see, regardless of how I wrote it as ln of 11 minus ln of 13 or ln of 11 over 13, I get the same answer. And that would be how many minutes it would take it to be cool enough to drink. And then you would just drink the whole coffee pot, and we don't have to worry about when it's too cold to serve. No, literally, I actually don't want to find that. It's the same exact thing that we did over here, except that we're trying to see when our temperature is going to equal 155, which, according to these expert baristas, would be too cold to drink. So same exact equation that we did over here, except with 155 instead of 175. And I feel like this is kind of silly. It's like the same thing that we did for double life, except now we're doing half life. So we're saying, well, what about when it ends up being half the amount of life? And same exact thing that we did before, except now that this is going to be a half. And there's kind of an invisible one right here, so we're trying to see what is k going to be when our 1 becomes half of that. So right here, I'll take ln of both sides, and I'll end up with ln of 0.5 or 1/2 is equal to negative kt. And I can solve for the length of time by dividing by this negative k. T is going to be equal to ln of 1/2 divided by a negative k, or I can put that in thinking about in front. I hope this has been helpful. Bye.